Yes, I think we need to think maybe about number densities and total number of objects to kind of see is it dense, is it not, is it dynamical. Because, for example, you can have like triple interactions in the field, which I don't think it's very dense. And also you could have other interactions in dense environments, which could be eccentric. And also maybe focus on how much gas do we have in these systems, because gas can really change things. So again, field and maybe old clusters are quite gasless, while younger environments are maybe have more gas. And I think the most like dense in all scale, both in gas and number of stars, is usually the active galactic nuclei, or AGN for short. And AGN has become recently quite interesting, mainly because of the vast amount of gas, you can allow some massive black hole growth. So maybe you can have like go beyond this mass gap. Also, even if you have two black holes merging, you can still have some EM counterparts because of the gas interactions during the merger. And also, even if you can have a strong peak after the merger, you can still be retained to the potential of the supermassive black hole, and therefore maybe have some hierarchical mergers. And people have recently started modeling these things. So initially it was very simplistic with some kind of like Drake equation modeling for the rates, and recently it has becoming more evolved. People have been doing this kind of population studies where they kind of like pick various processes and kind of try to bind them together. And because it's it's AGN with a lot of gas and stars and black hole, it's very dynamical and messy. And one of the key features is something that's called migration, and we're going to be focusing a bit more on that. So the idea behind that is that usually we think of this accretion disk as being some kind of Shapur-Sunyaev solution for this disk that goes back to the 70s. Usually starts from some low mass XY binaries, but usually you have some very inner zone that has a very increasing radial profile because of the radiation pressure dominance, and then it becomes decreasing once the pressure is becoming gas dominated. But for the very massive, for supermassive black hole essential objects, you tend to be gravitationally unstable eventually. So maybe in the outer zones, you're going to have a different profile, and you have to model it in a more careful way. So once we could have these kind of like simplistic parallel scalings, and then if we usually have these things, also if you have some object inside a gaseous medium, you could have some gravitational interaction between that object and the gas, and it will form, I think, as Christoph has nicely shown, some two wakes, maybe two spiral arms that eventually each arm will try to pull the object towards itself, and you're going to have some tug of war. And usually this typical torque is going to be depending mainly on the mass ratio of the small body here and the supermassive one here, and some properties of the disk, namely the scale height, the aspect ratio of the disk, which is the scale height over the size. And eventually, because you have two arms, they kind of compete with each other, so they almost cancel out, but they do have some residual torque that is weaker by a factor of the aspect ratio. And this is small because usually the disks are quite thin. But the actual number, the actual sign of the torque and the number will depend on the gradients we have in the disk, namely on the surface density and the temperature gradients. And if you take that and go back to your migration AGN disk stuff, usually you're going to get something like that. If you're going to look on the torque, so these red lines here, again, it's some log radius in some normalized units versus some typical arbitrary number for the torque. And eventually you're going to have some locations here that if you're like a black hole, you're going to move inward because you have some negative torque, and eventually you're going to stop here because here your torque is changing sign. And then the idea is that you have some black holes that move here, you have some black holes that move in the other way, they meet together, there's a traffic jam, it's all messed up, you increase the local density of black holes, which kind of forms some kind of mini cluster, and then they start to dynamically interact and hopefully allow more mergers. So I think that's the underlying idea why these traps could be important for this AGN channel. But it's a bit complicated. The last thing I told you is a bit simplistic. As you kind of play with mass and viscosity and other things, you're going to have many more effects which are hard to model. And one of the recent things that happened, at least in this field, is that there's been some identification of some thermal effects. And the idea is that if you have something that accretes, let's say you have a planet that accretes planetesimals and hits the surrounding because of some ongoing luminosity, it will change this local density profile that could actually affect the total torque. So that effect of changing Then local density due to some diffusion of heat is called thermal torques, and has been found in 2015 to actually stop migration of planetary cores during planet formation processes. So that was for planets, that's fine. And there's been some recent progress in the sense that recently there was a paper that basically kind of tried to apply this idea to also AGN disks. And the idea is that you have some stellar mass black hole that, well, it has a lot of mass influx, so it has some luminosity, usually almost any luminosity probably. And usually what happens here is you have like three different length scales, which are a bit confusing. So you have the outermost one, which is the scale height of the disk, which is quite large. You have the smaller one, which is this XP, which is the core rotation radius. Basically, it means that if you put a massive body, it will move in scientific velocity. If you take the same parcel of gas and put it in the same place, it will move slightly slower because you have some pressure gradient that affects that. So there's this bit offset, and you need to move a bit inward to get the right velocity for the gas and the solid particle. And there's some offset, which also causes asymmetries. And the last one is the length of this lambda, which is basically the length of this thermal diffusive blob. It depends how distant it can propagate. And if you're going to do the math and follow this ugly paper that has 157 equations, you should check me. You're basically getting that your torque is going to be depending something like that. You're going to have some luminosity ratio of your actual luminosity of your object versus some critical value LC that essentially depends on your thermal conductivity. It's kind of like a thermal diffusivity. It's kind of like a diffusion coefficient for thermal diffusion and some disk properties. And so we also have this physics underlying here. And again, once you overcome this critical threshold, you're going to have a positive net torque. So that thing could really change your outcome. So now we're ready basically to take some simple disk models. So I think the solid lines just have some simple Shokoshev solutions with some very simple opacity laws as power laws. So they're easy to generate compared to like more accurate dash lines. You actually have to solve the actual equations for the disk with capacities and blah, blah, blah. Anyway, so it's more accurate, but it takes much longer to generate. But I think qualitatively, at least, you would get like very similar behavior. And what we're getting once we have different disk masses, we're getting that at least in this area, we have, at least for the lower masses, we are getting some region where we have also positive torques once we include this thermal effects. And we can maybe try and do something better. We can maybe now have the ability to generate many more disk models. Maybe we can like fix the alpha viscosity and try, and basically just vary the mass continuously. And I'm gonna get this kind of nice picture. So basically there's like a point here that there are no sign change. So maybe just things just flow inside and don't stop. But also, at least in the lower mass, you're gonna have like some lines here that eventually these should be the new migration traps in some sense. If we have like a black hole here, it will move actually outward, while if I have a black hole here, it may move inward. And that location is not fixed anymore, but it really depends on the mass of the supermassive black hole and the other properties that we have in the disk. And we can do it a bit more general. It's the same triangle here, but now also color-coded like the typical migration time. And we see that indeed it is fast enough. That's units of mega years, hopefully. So things can really go here quite quickly. So we do expect them to be accumulating. And the last thing is that now we can generate these models quite quickly, and we can maybe try different mass and accretion rates, and we can like probe whether we have traps or not. We're doing it kind of like in a random way, like a few thousand models, and eventually we do see this trend that actually the disks that do have migration traps seems to be having lower luminosities, while the higher luminosity disks tend to not have these traps. And I think these lines are just lines of constant luminosity with some jumps. But this gray one is like 10 to the 45, and we also suggest some basic fitting formula that can depend on your alpha viscosity of the dividing critical luminosity. And it's actually independently, these people have claimed also that if you pretend that most of your black holes are coming from AGN disks, they actually won't be in the most luminous ones. So luckily enough, it was consistent with what they found. And I did not know about what they're doing, so it was, we didn't try to explain that. So I think that was the nice result here. Yeah, I think that's pretty much summarizes my work, at least on that matter. And of course, just to summarize, it's been very simplistic. We only had once black hole that moves, and in a disk, it was a very simple model. Of course, in reality, you have like other migration mechanisms like type 2 that has a gap. Maybe you have like binary black holes. So we don't want to take this in the future. We don't want to take this bit and look how it affects on populations and rates and properties of the AGN chunks. That's work I'm planning to continue doing. Yeah. Thank you.
I'm wondering if what predictions do you have about the population of merging black holes, except of them originating in AGNs, that might be characteristic for these kinds of models in terms of mass ratios or rates?
Yes, I think to be exact, you need to do some n-body coupled to this prescriptions to check that. So we're trying to do that, but at least one key point is could be, if these mergers will happen further out, maybe larger fraction of the major products could be ejected, for example, either from the disk or from the system as well, just because you're in a your escape velocity is much lower now because you're further away. So that could be an implication.
Sorry if I missed it, but so the origin of the heating, is that coming from like some kind of viscosity, some viscous heating, and then is it just assumed to be like an isotropic viscosity, or is there something more complicated?
Yeah.
Or it's dependent on directions?
Yes, so I think here in this case, you just, I think these papers, what they did is essentially you pretend you have like a point source of luminosity of some energy, and you see how it affects on the surrounding gas. And then you calculate your density distribution of these two blobs, and look on the kind of like the force that applies back onto this point source. And the original luminosity could be either some accretion of some solid material or some gas. I think it's more natural in the AGN context.
Are there any other questions? Still David sits up.
This may be a naive question, but are you assuming that the black holes inside of that Hill sphere are orbiting in a circular orbit around the center of the AGN?
The black holes? Which black holes?
Bodies.
Yeah. Yes, so usually the spiral wakes are going to generate here further than the sphere. You can have the scale height to be larger than the radius. But this thing actually happens well inside the Hill sphere. So I think that's originally why it was initially hard to simulate these things. You need enough resolution to.
But is the Hill sphere going around the center of the AGN in a circular orbit?
Yeah, I think, well, the bot just moves in a circular orbit. So yeah, I think the Hill sphere just centered on the center of the small black hole.
Okay, thank you.